All right, thank you. So let's get started. I know we've got a few folks to come in, but let's get going. It's almost 1:20. So I left you with a question, and I thought I'd start by explaining a little bit why, and then we can talk about what you're going to do and how you're going to help me. So here's the thought. You know, in today's world, gas turbines tend to be big and used for things like propulsion, and reciprocating engines tend to be used for small applications and sometimes grow into big ones. But I thought I'd show this plot. This is a plot of, if you're thinking propulsion, a mobile platform, whether it's on the ground or whether it's in the air, you probably want to think about power to weight. And this is where gas turbines typically excel because they're very compact. They don't need to have the same number of auxiliary systems. They don't have the equivalent of a crankshaft and connecting rods, things that are pretty heavy. So this is a plot, non-dimensionalized, but it's based on some real data of particular gas turbine and then a few reciprocating engines. And what you notice is reciprocating engines can be much more efficient. So if you ask the question, why would you consider a gas turbine for a lot of applications, you probably wouldn't. And especially if you look at a gas turbine at part load, its performance falls off. As I said before, once you're at full speed, your shaft is turning at its desired speed, and you're pushing all the air through. So all the losses associated with compressing and expanding air are true. And then as you add more fuel, it gets more and more efficient to its peak point. So if you have an engine that needs to vary and load a lot, reciprocating engines are even more valuable. But if you're in a hybrid electric situation where my primary conversion to traction or thrust, whatever it is I'm doing to create the work that I want, if that's electric, now and say I have a little bit of energy storage, I now have a choice of how I run the engine. It's not, that direct linkage isn't there. And so with that, it's an interesting thought to think about a gas turbine. It's already lighter and more compact. It's less efficient, but if you're only going to run it at high power, that penalty is not as high. And imagine you thought about something that started to get more efficient. So that's sort of the thought experiment for today. We're going to design an engine, or design at least a combustion system for an engine that would be better power to weight, maybe not as efficient as the best recip I can think of, but gets competitive in this hybrid electric. So that's the thought. And then the problem to solve then is, so how do we start? And that's really I want to work through what are the requirements, what's the thought process, and what you're going to do with your groups. I'm going to have 10 questions at the end, and you're going to be given an A versus B choice, and you're going to get into groups and debate A versus B, and then we'll have a conversation as a team. So I wanted to come back and say, here are some of the considerations, and so think about those considerations. You might want to write some down, because you're going to get a question, and then when you're given an A versus B choice, there may be, well, it's going to be great for this, but what about that? And then that'll be the trade discussion that we can have. So that's where we're going. And to start with, I just wanted to spend some time talking about requirements. And bear with me because I'm using instead of a blackboard, I'm going to use a stylus here and write on the board. So you're going to see my handwriting through a stylus. And if it's not working, tell me. So first of all, if you sort of think about the top 10 list, what does a combustor have to do? Help me write a list of requirements. Has to diffuse the flow, okay? And why is that important? Okay, actually, and that's awesome. I was going to get to that later, but I'll put diffuse the flow because that's an important point. Okay, let's talk about the function of the combustor. Why do we have a combustor in the first place? Burn the fuel, okay? So really, I've literally had these design conversations. Someone says, I got a great idea, and let's say the combustion efficiency is 98%. Does that feel good? 98% combustion efficiency? So that is awful. And there's two reasons why it's awful. First of all, we do all this work to make efficient cycles. And we try to control losses and have efficient components. But if I'm not burning the fuel, I'm going to have all those unwanted products we talked about, CO, unburned hydrocarbons. So you really want to be very high efficiency, way more than 98%, to be a practical and useful device. There are cases, if you look at an old two-stroke marine engine that goes in the back of a fishing boat, okay, those are not very efficient. But that's because people aren't using them for many hours in a day necessarily, and there are reasons why they chose that. But for most engines, got to be much higher. What's another requirement? Because if you start with the requirements, then we can think about a design. So other requirements. Sorry? Yeah, so achieve the, in fact, I'm going to build on that and just think about get the right temperature for the turbine and temperature distribution, okay? So I'll say acceptable, and all of these things can be turned into numbers. But there's a notion called profile and pattern factor for an engine. And because if you're a turbine designer, you don't have to have the temperature be perfectly uniform, but for sure you have to know what it's going to be. So I'll say acceptable temperature for turbine. And for example, if you make the combustor too short, you might end up with really hot streaks, in addition to other problems like maybe incomplete combustion. What's another key requirement? In the end, mixture ratio, so tell me more what you're thinking. Is it the degree of mixing? What is it about the mixture ratio? So if it wants, so I'll just say, and again, I'll use the term acceptable mixing. If it's a rich combustor, it may get a different requirement to be acceptable versus lean. And I just wanted, where my head went when you said that was, in the end, the fuel-to-air ratio is given to a combustion designer by the cycle. The cycle is going to say there's this much air, you got to make the power we said we're going to make, you're going to add this much fuel. So in the end, the overall fuel-air ratio is given to us as an input. But as a designer, my requirement then is to take that fuel-air ratio and decide, for example, how hot to make the reaction zone, right? Where to put the air, and I can move that air around. Other requirements. So I gotta have acceptable durability, and I could write the word acceptable, but I'll just write durability. So durability is, there's an expectation it's going to last for a certain length of time, and depending on the mission, as I said, we have aircraft engines that have been on the wing for 5 years. It used to be acceptable for an industrial gas turbine to last for 8,000 hours of operation between sort of inspections and some sort of maintenance. But if you think about it, 8,000 hours is only a year. And if it's a base load unit, it might accumulate that. So do you really want to be overhauling your engine every year? So now the industry standard, it went to 12,000, but in the end it's had to go to 24,000 hours because that's as good as the turbine folks can do. So you kind of want to line up all the parts so there's one sort of overhaul period. So this isn't true for every model of engine, but I'd say to be a desired outcome for every engine is to be something like 24,000 hours life. That would be considered good. Let's talk about performance. I showed the Brayton cycle, the TS diagram. What's another thing that's important when you think about the combustion system? So turn down becomes very important. And that's so that I can run at part load, right? I can run at whatever condition I want to. Other parameters. That's where I was going, exactly. So what we call dP over P. So I have a delta P across the combustor, and I have a certain pressure that I'm at, and a typical number for a gas turbine would be 5%. And so sometimes the combustor is the limit, sometimes actually the cooling system for the turbine makes a minimum. But from a thermodynamic point of view, 0 would be good. In fact, pressure gain would be awesome. And there is work around pressure gain combustion systems. Great. What are some other requirements? So that gets into what we call operability. Okay, so a combustor can be inoperable if it has high combustion dynamics. And actually there's a coupling between operability then and durability. There can be one phenomenon that affects more than one requirement. You're actually doing a great job. I got a list I'm looking at, and you've got 8 of the list I'm looking at. What about when you buy a machine? What's important when you buy something? Fuel. So are you sure that the fuel you have is the one that you're going to always have, right? So especially for utilities, one thing that I didn't realize until I was in this industry, but if you want to build a power plant, often you're using someone else's money. And so it involves a bank. It might even involve insurance folks. And they only care about one thing. Are they going to get their money back, plus some reasonable return? And so they worry about, is the machine itself going to be reliable? But they also worry about, what if that fuel is not available? And you had to burn something else. So fuel flexibility is sometimes more of a theoretical construct than it is practical, because actually a gas pipeline might be very, very reliable. But in order to get approved for that bank loan, you may need to show that, well, on a bad day, I could burn a different fuel. And that often drives some of the design. Other thoughts? Geometry. So tell me what you're thinking. Perfect. So you got to integrate to the rest of the engine. So it's one thing, and turbo machinery designers have lots of interesting thoughts. The kind of thoughts they have, if it's a compressor, is it an axial compressor or a radial compressor? And so the air either comes straight at you along the axis of the shaft, or it might be radially outward, and then it's got to turn. So it's got to be, I'll just write here, compatible with the engine. Another one. So that's a choice, and I think that doesn't well, sometimes it's required. It could be that don't make an engine bigger than something. If an aircraft engine, it's got to fit inside the compartment that's been designed. A ground-based, there tends to be less constraints, but still, it can get down to, does it fit in a shipping container, stuff like that. But I would say when it comes to reverse flow, that isn't a requirement. That's a choice that a designer will make, and we'll talk about that later. Yes, of course. That's what we spent a lot of time today talking about. And there's many types of emissions, right? So it could be NOx, but it could be CO, it could be unburned hydrocarbons, it could be particulates. Yeah. I'm sorry? Yeah, so I put that a little bit with what we called operability, so I'll just add it here. You said static stability? Typically that, it doesn't have to fit here, but it's part of operability. Is it operable over the range you want? In the back? Absolutely. Right? So what I've learned is engineers are very creative. And actually, they become very creative when you tell them cost is important too. But sometimes we want to add features, and we really have to, a lot of conversation becomes around, does an idea buy its way on the engine, right? It can be a great idea, it can even work really well, but is it worth the cost? And the cost sometimes is actual money, the cost can be weight, it can be a cost in reliability. So there's all these things you got to think about. But ultimately, if you're going to sell something for a profit, you got to make sure you can sell it, you can make it at a reasonable cost. I think we've got a great list. I'm just looking at my my list here. I think you got a couple more I didn't have. Anything else anybody wants to add? Sorry? Insulation. Could be. So and that really is, it's really integration with the engine. So whatever the engine needs, it may require insulation, it may not, it depends. One more in the back? Sorry? Power out? Yeah, and so I'd say in the end, that translates to, typically, that's an engine requirement, but it's really the fuel to air that you got to be, it's got to be about your T exit for your combustor, right? It's whatever the cycle is demanding of you to achieve that. One more? Sorry? Control, absolutely. So that gets into operability. So I'll just put controls here as well. I'm learning how to write the pen here. Great, so that's not bad. So we've got a really good list here. Let me jump to the next page. And I think, because I have, once I learn how to change pages here. And next. So here it is a nice tidy list of what I came up with. And I want to give credit to a lot of this section I'm talking about. In fact, I'll show you. There's a fantastic book that if you're interested in gas turbines, there's a book called Gas Turbine Combustion. So Arthur Lefebvre, very well-known person in the field. I had the pleasure to meet him a couple times. He was visible at conferences. He went around to companies and paid visits. But he's one of the people who just did an awesome job of collecting the information that others put together. He also was very active himself and had a research group. But Gas Turbine Combustion, this is not the newest version. I think there's a new one. There's also a great book, Atomization and Sprays. But a lot of the material I'm using this afternoon really is pulled from this book. It really sets the standard and just gives the right fundamentals. So I wanted to just go a little deeper on a couple things before we go into our exercise and really help think through sort of, and somebody said this already, what does a combustor need to do? And what are some of the important things? So if you think about the simplest implementation, I have a duct and I have air going through. And this could be an annular duct, say what's coming out of the compressor. So if I want to squirt fuel in, one could imagine if you're trying to make the simplest combustor possible, you would simply stick a fuel nozzle in and it would spray some fuel in and we'd be done. So help me out. What are the things that are not good about this as a thought as a combustion system? What would be the limitations compared to that requirements list? Absolutely. So actually, we've got to draw this a little differently. And why is that important? Why is it important to slow the air down? Well, there's actually, we'll get to that, because this, I'm not sure, this may help, but will it be good enough? The thought I want to leave you with is a critical curve around, we said that delta P over P is very important, and if I were to talk about the velocity, and I'll put it in terms of Mach number, the Mach number in the place at heat addition. So the Mach number when I'm adding heat. Is that a steady curve, or what do you think it does? It decreases? Actually, it does the opposite. If I'm very low velocity, I can add heat to air and life is good, okay? But if I'm high, and actually it's a quadratic. So if I'm much, and on this curve, I'll just give you some typical numbers. If I'm Mach 0.1 here, I'll be about a 1% pressure drop. So even if I'm aerodynamically beautiful in terms of not having flow structures that cause pressure drops, just the fact that I'm releasing heat into high velocity fluid. And so if I get to a Mach number of 0.2, I can be, I'm just looking, and it depends how much heat I'm adding. A typical heat addition would be temperature ratio on absolute coordinates of about a factor of 3. That's why the density will change. But I could go all the way up to 6%. So if we have a budget of 5%, and I said I want to be an awesome combustor, right? I'm going to be high velocity. I'm not going to take that air from the compressor and slow it down, because why would I have a diffuser and all that claptrap? Well, I've suddenly lost my pressure budget, right? Just because of heat addition at high Mach number. So fundamental thing, you gotta slow the flow down, and to something below Mach 0.1 would be a good rule of thumb. So do we have a combustor yet? Is what I drew going to be stable flame? And what's an example of a flame stabilizer? A bluff body. So if I just simply put a disk in the middle of this flow and made a bluff body, now I'm going to have some sort of recirculation zone. And actually, that's not bad. That would probably be the minimum acceptable. And then what are the kind of things when you have a bluff body stabilized flame? And actually, this is similar for swirl stabilized. But what are the things I'd have to worry about with that stabilization? Sorry? Yeah, so I can have a vortex. I mean, that's a swirl, right? I can make a swirl with a vortex, so it would, in the end, have a similar thing. Where I'm going, and I'll just draw the curve. You end up with if I think about velocity coming around the outside here, and I have this stable flame, in the end, I have a stability limit. So if I have an equivalence ratio, if I'm equivalence ratio near 1, I can maybe withstand a pretty high velocity, and the thing will stay lit. But if I go leaner, I end up finding that the velocity as a function of fuel-air ratio, where it starts to blow off, goes down, and the same thing happens on the rich side. So I ended up with a region, I'll show you the outside, where it's blow-off. So we need to make sure we don't have too high a velocity. And the reason this is important is this might be a curve at full pressure. And usually you start a design at my high power point, because that's a great place to start. But think about it. If you have a gas turbine that's a pressure ratio of 20, it also has to operate when it starts. And that means the pressure ratio is much closer to 1. I'm just turning the engine over. I haven't yet reached choke flow. So there's another stability curve at low. So this could be my high pressure point, and this becomes my low pressure stability curve. So really, when I think about the flow in this system, I've actually got to worry about this curve. And then I got to say, oh, and by the way, I'm not actually free of one, because that would be high temperatures and maybe high NOx. So now I'm somewhere leaner. And now I've got to be thinking, okay, what's that velocity for my flame stabilization method? So, so that becomes something to worry about. Think about the other requirements that we have. What's the other issue? So there's more issues. We've got to sort of add more components. What's another component you want to add to what we've drawn? Fantastic. So imagine that if this is sort of the out on the outer, I'll have to say this is an annular combustor and this is the outer part. That's the casing. I need to put a box around this because I don't want that flame to have hot products hit the wall of my pressure vessel. One of the fundamental parts of a gas turbine is typically we have cold structures that take the pressure and we have weak structures that take the temperature and and maybe handle the pressure drop across the combustor, but they don't have to withstand the whole pressure ratio. So we've got to start to put a boundary around this thing, and that then starts to look like the cross sections you've seen. You've got some sort of structure and casing. This might be the outside world here. Inside here, there might be a shaft that's rotating, and we got to protect that shaft from getting too hot. So we're almost done. What else would we want to maybe try to improve on this? Absolutely. So it's all about what's the temperature to have a stable flame, and then what do I do? And if I was more capable, I would get an eraser, but I'll just put an arrow here to imagine we had drilled holes and we have some air, the rest of it. So really what this gives me is a degree of freedom to say in this region, I'm going to be having the right fuel ratio for very stable operation. I can ignite it. It can be happy when it's at low power. But then I add the air to cool it to the temperature the turbine needs, and then I can tune it. I can also do a little bit of tuning of that profile. So these are some of the main ideas and thought processes that we want to go through. So let me just see if there's something else I wanted to mention. The other thing that gets into, if we're trying to fix the length, what are some of the factors that would be important in terms of the overall length of our system? So I heard residence time, and actually, so here's interesting. Residence time for a combustor is the volume divided by the volumetric rate of air. So if someone said, what's the residence time? You could ask the question, well, give me a CFD, I'll integrate, and I'll figure it out based on integrating some complicated set of measurements. But very simply, if I know what my compressor is putting out in terms of how many pounds or kilograms of air per second, and I know the temperature and pressure, so I know density, I know the volumetric flow. And if I know how much air is going into my combustor, then residence time at the macroscopic level is simply the volume of the combustor divided by that volumetric flow. So it can be very easy to calculate bulk residence time. So that's important. And when we think about that, so let's put it in terms of time. And actually I'm going to do one over time. What are the factors, or I'll just add. What are the factors of time that are important when I think about just how much time I need? So there's time for the reaction. And you're right, CO tends to be the slowest one. So if I have a CO requirement, I got to make sure I'm respecting that time scale. And if you think about it, I talked about the fact that at low load, you're at low pressure. I have to respect the time scales at low pressure, not just the ones at full power. So time scale for chemistry is important. Sorry, showing the old one. Here we go. What other time scales do we have to worry about? So if it's liquid fuel, I have to worry about vaporization. because it's really hard to start mixing until it's evaporated. And there's one more time scale of the. Yeah, well, we're trying to add up what's the total residence time that we need, right? So there's elements of that. And we just said it, right? Together with evaporation, the next one is mixing. So to first order, I need to make sure that I've got the right combination of velocity and length to give me times that add this up. And so what you can see is just with some really simple thinking, you can start to lay out a design and just keep a few things in mind. You know, how much time do I need? And this is where you can go back to some of the Chemkin, you know, sort of calculations and subroutines that were talked about. A plug flow reactor, a perfectly stirred reactor, those can start to give you the times to guide how you think about the aero design. And then once you have an aero design, you can think more about the mechanical packaging and durability. So those are some of the main ideas I want to talk about. I now want to give you a chance to break up in groups, and I have a exercise for you. And so I'll pose the questions, and then we're going to come back and you're going to talk about them. So to help with time, you know, if we had more time, we could make this a more open-ended discussion. But for each group, so everybody knows what number you are? Anybody not know what number they are? Okay, so whatever number's on your tag is the question you want to focus on. You can look at the other ones too. And I just wanted to start, we start with things like architecture, how we're going to stabilize the flame, fuel or mixing, and there's just a couple of choices that you have. And so imagine you're new hire into a company and someone says, look, we're in a hurry, we have to get a proposal out by Friday, we need you to look at this thing. And when we put together our final proposal, you need to help us. So that's what we're going to do as a team. You're going to break up now for the next few minutes. And then within your group, I want you to discuss and debate which choice. And then you're going to have a representative of your team, and you collectively are going to define this combustor. And then we're going to talk about what we like about it and we feel good about, and what are the areas where we think there's risk. So that's how we'll start. I think for this discussion, I mean, you're welcome to stay in your groups here. Let's give you 10 minutes, and then we'll come back together at 2 o'clock, and we'll just go down and be ready to explain your choice.
So just to clarify, it's let's do A 1 through 5, and B 6 through 10, because they're grouped up, A and B.
Oh, perfect, okay.
No, it's A 1, 2, 3, 4, 5, and then say B 1, 2, 3, 4, 5.
Oh, so you're saying we have 2 groups in the end?
No, there's still 10 groups, but they're not numbered 1 through 10. They were A 1, 2, 3, 4, 5, and B 1, 2, 3, 4, 5.
Oh, got it. Okay, so it's A1, A2, A3, A4.
A5, yeah.
And then B start at 6. Got it. But your choice in each one is A or B for the question. All right, so you got 10 minutes.
He wants to know what's the target for the gas turbine.
It's the one we talked about before. It's the hybrid electric small gas turbine that's going to wipe recips off the planet for these applications. That's our mission today. Okay? All right, so I'm going to call on each group here. Group 1A, tell us what combustor architecture we're picking and why.
Okay, our answer is it depends.
Okay, by the way, that's not allowed, okay? So if you want to pass this section, you're going to pick A or B, because actually, I'll tell you, there's no wrong answer except that.
Okay, so if because you are giving us 2 options, right? The VTOL and the truck. But if we just pick one, we will go with the A, annular.
Annular, okay. And we're going to talk about these later. So, but I do want to get to, and I know it's, a little bit forced here, but actually this is like how design gets done. You pick stuff and then you start to debate whether you like it or not. Okay, group 1B, flame stabilization method.
A2. Yes.
So it'll be swirl stabilized. That's what we are going with.
Okay, most gas turbines are swirl stabilized, so that's a pretty safe choice. Okay.
Yeah. Better mixing and better control over the recirculation zone. That's what we're going for.
Yeah, and we'll talk about this more. Most gas turbines are swirl stabilized, and they also suffer hydrodynamic modes and instabilities because they're swirl stabilized. So those are the trades. That's what you're signing yourself up for when you pick swirl stabilized. Final answer? Yeah, no, it's fine. All right, group 1, A3. Fuel air mixing.
So we'll go with lean mix, premix,
You're going to go lean premixed. All right.
with a lot of factors. If it's VTOL, we will go with lean premix. If it's a truck, we will go with diffusion. But to give you one answer, it's a lean premix.
Interesting. So I didn't tell you all the information. I will say this, that the ICAO standards are only for engines, I believe, above 2,000 pounds of thrust, and we will be well below that. Okay. But there's still good reasons to pick lean premix. I'm just helping you. And we'll talk more later. I just want to get all the answers on the table. So, group A4, combustion liner cooling.
We are going for choice B, so wall effusion.
Okay, so you want to pay all that money to drill all those little holes in the liner.
Yeah,
good for you. Okay.
I know that, but it's more efficient. Okay.
And that's okay. Like I said, every choice is not wrong. It's just every choice has a consequence. Okay.
Group A5, we are going for 99.999%.
All right, you guys are in.
Yes.
It might be kind of heavy to be that long, but that's the choice we're making. Okay, we're going to put that on the brochure that we have like no unburned hydrocarbons. It's going to be good.
Okay.
All right, group B1.
Okay, given the size of the combustor, since it has to be kind of not very big, so we think the drop can be about 6%, given also it has to have high flow, because the Mach number can be higher, and that's, even though 4% seems better, practically we think that 6% will be a better choice. So
that's an interesting choice. And it's certainly going to make it easier for the combustion designer, especially our cooling friends. But we do want to beat recips. So a little more loss is going to hurt us in beating recips. But that's good. Well, it's a starting point. Today is just a starting point. All right, combustion liner material. And for those who don't know, let me explain what I'm saying here. There's different grades of stainless steel. 316 is one of the more capable, and it's expensive compared to regular steel, but it's pretty cheap stainless. Compared to things like Hastelloy X, which are used in commercial engines today. So, what choice did you make?
So based on the application, which would be relatively simple, we'd go with stainless steel, since the maintenance cost would be much less, and the initial cost would be very low.
So that's and that's the kind of trade you want to think yourself through, right? This is lower capital cost, likely, and if we're trying to beat recips, recips are known for being inexpensive engines, so how do we get there? All right, B3, velocity in the fuel air mixing region.
Okay, we will choose 80 meters per second, so that we have higher residence time. Particularly if we are talking about liquid fuel, so that vaporization and mixing, it has enough time. So
okay. Yeah, and the debate will be, you've chosen a lower pressure drop, which is awesome. So that'll help our 6% friends. And yeah, the question will be, flame holding and flashback in that region. But you might be okay. 80s probably on the good side of that boundary. All right, we got to ignite this thing. How are we going to ignite it?
We were considering, first our choice was a spark ignition. However, since we believe that the cost of ignition system to the total cost is not high, we can afford 3-time cost. And since the combustion will be lean premixed, we think the choice of laser ignition will be a better choice to have a higher operational range.
Very cool. So we are going to try some new technology on this engine. Excellent. And the last one, what resonance time are we going to pick? Route B5.
Yeah, I think 4 milliseconds should be okay, because like 15 milliseconds is a little bit on higher side, so the knots may form.
So great. So, this is, I know we've done something in half an hour and we've sort of pushed it a little bit. Let me talk about some of the trades to make. And then, what's fun about doing this is if you were going to go build this, first of all, you got to choose stuff. So for those who have a hard time choosing, it's okay. And what you do is you learn what you're signing yourself up for. Sometimes you keep 2 things in play, but I will say that you can't put off, if you want to get to a product at the end, you got to make choices. And if you just work 2 things, in the end you get half as far on each thing than if I just picked one and made it the best it'll be. So that's what's fun about this. Let me just give you some thoughts to think about. An annular combustor, and I'll just reflect on some of the things I mentioned earlier. How do I fix this thing? Now, it's a little engine. That's a good news. So compared to a big engine, if it's going to be on a medium truck, it's probably something that's actually not that big. So if you're trying to do maintenance, not a bad choice, because I could tell my customer I'm going to swap engines when you have a problem. So even if it takes a little bit longer to fix, it's going to be good. The other value of an annular combustor for this application is it keeps it small and lightweight. This is the most compact form of combustors of the choices you've seen. And it also means the temperature profile into the gas turbine will be pretty uniform as well. So this is probably the best choice for a little engine and for keeping it simple. In terms of flame stabilization, you picked Swirl, and that is the way most gas turbine combustors are stabilized, and for good reason, because what's good about having a swirl, then the debate becomes what swirl number and how strong is that recirculation zone. But the good thing about that is you end up with a aerodynamically stable structure that probably doesn't change a whole lot over the operation of the engine. So I have a flow structure I know and understand. One of the problems with you can get into is, for example, the flame may be able to sit in more than one place and during the operation. And if it's ever near a boundary, if I'm in location 1 versus location 2, what that means is it can bounce around. And that's a form of instability that is undesired. So having clarity of where I want to have the flame be stable and have it be a structure that's stable over the operating envelope is very valuable. But I did mention when you mentioned this one, right, swirl, if you have a swirling flow, you end up with a processing vortex, and that does interesting things in terms of heat release spatially and how that may or may not couple to an acoustic mode. So that's a watch out, but it is overall it's a good choice. Fuel air mixing. So this is an interesting one. If you're trying to make the simplest, lightest, cheapest engine, diffusion would be a good choice. But it does have higher emissions, and you end up having hot spots. So even you may think I have a simple combustor. What's nice about a lean burn system is the peak flame temperatures aren't high, which also means the contact with the metal isn't so high. And so I can actually have a more durable system if it's lean. The issue is, can I get through all the operability and controls? So the tension in a design team on this one would be, how do I achieve operability over the whole envelope? Do I need more than one fuel circuit? You know, can I do it with a $10 Arduino card, or do I need something a little more expensive for controls? Again, we're trying to make a small, lightweight engine, so we want the controls as simple as possible. So that's the challenge that the team would get into picking lean. It's a great thing to put on your brochure. If you're trying to sell this thing, you want to say it's a low emissions engine. It just, whether the regulations apply or not, it's great to be able to say that it's a lean and efficient engine. So that's a good choice. Liner cooling, you know, given that your friends pick 6%, you could probably afford a reverse flow. But reverse flow is more metal. It's more weight. Going with a fusion wall cooling is good. It does add cost, and it depends how you put holes into the material. There are different technologies for drilling lots of small holes, but all of them are fairly expensive. So this type of component can become more expensive, and that would be the trade for such a design team to go work. How do we do this with lowest possible cost? But in terms of durability, in terms of being lean premixed, some sort of wall cooling is certainly desirable. Combustion efficiency. So look, I think, again, this is in the same category as emissions for me. You know, you want to be as clean burning as you can, but there is a cost. This combustor would be bigger. And if you were part of an engine design team, there might be a design team that says they have a goal for weight. In the end, they split that goal for weight into different groups. The combustion group would get a choice. And choices combustion team makes also affect others. So for example, if you have more residence time, which is what this, what we're really saying to get the combustion efficiency, it might mean the engine's an inch or two longer. So it's not just the weight of the combustor, it's the weight of the casing, it's the weight of the bearing structure. With rotors, you get into rotor dynamics, you get more modes and more interesting modes when the longer shaft. So you get into engine integration, and then that's where you get into why are you making this choice versus another, and how does it interact. But as starting points, these are great places to start. The pressure drop, 6% is making your life easy, and because you can afford to do reverse flow, you can afford to do lots of things. But you are making it harder for the cycle performance person whose job it is to meet whatever efficiency requirements. So this would be probably a good point of discussion in a design team of what's the trade, what's the benefit of being 6%, because there are benefits in terms of durability. You got more air to do cooling with. There's some advantages to having a high pressure drop, but you are hurting yourself from a thermodynamic performance point of view. So that trade, you need to get to derivatives and really make sure you want to stick with that choice. The combustion liner material, obviously and I decoupled it here, but the choice of material also goes with the temperatures of the cycle. They go with the type of cooling I pick. Things like 316 stainless are fairly easy to work, so that's good. If I'm trying to put holes, I probably want to put it in that material. And it's all about, can I meet my minimum requirement? Today I didn't give you detailed requirements around how many cycles or how many hours, so we don't have a good way to judge that. But I did give you a sense of the cost versus the life, and what we're saying is maybe life isn't the most important thing at this point in the cycle. We're trying to get an engine that works. It's trying to find its niche, and then if it needs to be improved, you can do a material swap later. So this isn't a bad place to start. The velocity in the fuel air mixing region, so a lower velocity is consistent with a lower overall pressure drop. And like I said, the only thing you got to think through on this one is, I like to have, actually it's easier to mix. One thing you may want to think about is, generally if I have, say, a fuel jet and cross flow, the higher the velocity, the more intense that mixing, the more energy I have to help get that mixing to happen. Picking a lower airflow actually maybe hurts that, but having a lower airflow slows everything down, maybe gives me more residence time per unit length. So the mixing trade is not necessarily so clear. You do have to think through auto ignition. You have to think through what fuel am I using, or if I'm trying to be fuel flexible, what's the most reactive fuel that I'm using, and will it still work when I put it in this engine? So those are the trades to think about. But 80 meters per second is in the ballpark of what people use. Ignition system, that was fun. I enjoyed to see you. It's obviously a technology group here. If I was with a design team in the industry, they would pick spark, and they'd be dragged to consider something like spark ignition. Laser ignition. Lasers are really interesting. What's interesting about a laser is you can project the energy away from where it emits from. And so if I, for example, have a recirculation zone, I can focus the laser so that it's igniting in the recirculation zone. Typically, most engines today, most gas turbines today, have a spark igniter that's over here on the wall by the liner near the casing, because they want to be able to swap that igniter in and out. But you don't necessarily have the right fuel-air ratio for ignition way over there. And by the way, it's separated from the stabilization zone. So the flame has to be able to make its way back to the stabilization zone. So sparks are great because they're cheap, they're reliable, but they actually make the life of an aero designer for combustors harder. And as lasers get cheaper and more reliable and maybe more compact, they may start buying their way on the engine. And if you're actually going to make this product, you got to have stuff on your brochure about why you're so interesting. And this could be a great brochure item. The risk is if they have lower reliability, then that can hurt you. But if they have all the advantages, like we've been talking, that you ignite in the right place, lights every time, maybe it helps ignite different fuels, then a laser is a great choice. And then the residence time, I think the 4 milliseconds and the 5 nines of efficiency are in conflict with each other. So those sub-teams would have to duke it out and really decide what's important. But 4 is great from the point of view of it's probably a more compact system. In today's world, that's considered acceptable for aviation. For a small engine like we're talking, it probably wouldn't be as high a pressure ratio. So again, 4 is sporty, and if I were to sort of just say what do I think is risky in the choices we've made, I would think that this is risky, the laser is risky, the really high efficiency is risky. And that's okay. When you make a design, it's all about making choices. And if you take no risk, you're probably not going to be differentiated, and you'll have a Me Too product. So really, when you're in design, it's really about picking where you want to differentiate. But you have to be ready for your competition to do the opposite. And when they do the opposite, and they say how good their choice is, you have to be ready to say why your choice is the right one. And like I said before, I've said many times, for me, some of these choices, there's not really a right and a wrong, but we can add all these up. We can start to have things like cost, weight, reliability, development risk. When you start to add those up, you can start to get a sense of what you're signing yourself up for. So that's where we've landed. I think it's awesome. I want to take, really the next time, I've got more I could tell you about design. I've got 2 things we could do, so maybe I'll open up to you to help me vote. I've got some interesting material on pressure gain combustion, but I'm also very happy to spend time just talking about combustor design in more detail. So let's pass the ball around and help tell me what you're thinking.
Well, I think it'd be great to ask some questions. So I'll start.
Okay.
Yeah, I just want from a practical perspective in industry. You talk about having teams that do different portions of the design, like we had different teams here, and I just wondered logistically, how does it work? So, teams probably have a project leader, and then the leaders get together and discuss, and who ends up making the decisions, and how does it actually flow? And in the end, when you have a design, how do you empower those engineers who worked in the teams really to get their ideas to the final phases?
Yeah, so I think there's many ways that it happens. Many companies have different cultures. I think some company, and actually even within a company, you'll have different design teams with different personalities. What I can talk about is different ways and then strengths and weaknesses. So, you know, what can be very simple for a team is to have a very strong leader with strong opinions. And they would look at a list like this and say, this, and they'll make all the choices. And if you're lucky, they're going to be right. But if you want to make world-leading products, often, you know, one person is not smarter than a group of people. So I think a fundamental discussion in any team is the group smarter, as a group, smarter than any one individual? And I prescribe to the group is smarter than an individual. Because if someone is very strong and just makes declarations, how do you know they're right? How do they know they're right? Are you really debating the ideas? So successful design teams, in my experience, are ones where ideas come from anywhere. Now, it does help to have passion. It does help to have people with opinions. Laser ignition, they're all in, right? Then the other part of the group has to say, well, why would we do that? No one else has done it. Why would we want to be first? Those are the kind of debates that a healthy team will get into. Just to help you think through how teams are organized, typically, I've been through a number of design cycles on a number of different engine platforms, and typically there'll be groupings by capability. So in combustion, the simplest separation is the mechanical design and mechanical engineers, sort of, and the aero engineers. So there's people who worry about the flow path, and then there's people about the parts that then constrain and define that flow path. And I've seen actually very interesting different organizations. Sometimes you'll see those specialties in separate groups reporting to separate managers. And, but they'll come together as a team, a co-located team, to do a particular engine development program. Sometimes I've seen it where we've organized where actually both are mixed. They report to the same leader, and they also subdivide. Once you get divisions beyond sort of aero and mechanical, you get specialization like heat transfer. And heat transfer is interesting because on the one hand, it's sort of an aero technology, but it has consequences for stress in life because how you cool is a big factor in terms of, well, where am I in terms of my material capability? And if I get thermal gradients or I get engine transients, so how heat transfer couples to both the aero design, because generally a heat transfer person wants more cooling air or more pressure drop, but that's going to hurt the cycle. So there's a healthy tension, and sometimes you'll take a team and actually divide it a little bit like today and say, well, you own this, you own that, and then you come together and you sort of find out where you start to bump into each other and where the trades are. So having groups that are having expertise, and I will say it's important that each member team has depth in something. So they have things they know, and then they have things that they can ask good questions to others who know other things in more detail. So typically, a combustion team, I've seen groups as small as 5. For a gas turbine, I've seen groups for a combustion system as 10 times that, 50. So it really depends on, are you making new technology choices and trades and studies, or are you just sort of doing requisition engineering and applying the design rules you have to a new application or a new maybe size or something? So the size of the design team actually is very much connected to how much technical innovation and risk you're taking. So I'm just trying to think other thoughts about teams. But really the best teams are one where it's a diverse set of backgrounds, where the team is involved in making some of the decisions, and that there's healthy debate. Because like I said, especially in combustion, there's not really a right and a wrong answer. It's really about what's working well, what are the risks, what are those trades.
Okay, I have a question here. You have described a lot about the thermal efficiency or thermodynamic efficiency. There is another efficiency for gas turbines that is really relevant also, which is the propulsive efficiency. And we see some other companies doing a 3-spool engine. They do open rotor, and they do like geared turbofan. So all of that would increase the propulsive efficiency. Overall, it will improve the performance of the whole device. So is GE taking one of these directions, or looking into these?
Yeah,
ideas?
so really when I think about sort of propulsion, right, you have chemical potential in the form of fuel, and really there's two aspects to it. There's the thermal efficiency of the basic energy conversion device, and that's where combustion comes into it. And then you're right, there's how you take that torque. In the end, most of these systems develop torque, and then where do you apply that torque? And conventionally, the simplest engine takes the torque from the low pressure turbine, runs that through a shaft to the fan, and it turns the fan. And that's true until you start to say, I want bigger bypass, which is bigger diameter fan. And then you say, wow, the speed of that fan wants to be slow, so my tip speed's not too bad. But now my low pressure turbine isn't as efficient if it's turning slow. So how do you manage that trade? And so that's been the art, I would say, as people make those trades. So one is to decouple and to have a gearbox so that you have the fan turn at the speed it wants to be, and the low pressure turbine turn at the speed it wants to. And from an aero performance point of view, that's probably a good place to be. But now I've added an element that has weight, it has cost, it has oil, it has heat transfer. If you think about how gears work, they have to mesh, so all the torque goes onto gear teeth. What happens when you have a really hard landing or other upset conditions? So you just have different elements of risk, fundamentally. But you've made it's been a sort of risk-off trade for the aero designer, but now the risk is somewhere else. So I think where you're really getting to for propulsor efficiency is what happens as bypass ratio goes higher, because that's really the game. And the ultimate, a good intermediate stop would be a gear. But at some point you say, why do we even have a fan? In fact, if a fan's so big and I want to have a contained fan, why do I want to have all that drag and carry around all that weight? Let's not contain it anymore. And then you go to open rotor, which is a lot like propellers. Now they have different shapes and names, but in the end, open rotor is not that different from a propeller. So I think that's the discussion. But those are great trades, a lot of intense debate in that industry. But in the end, the combustion guys aren't a relevant part of that conversation. Our job is to help create the device that creates the torque, and then we can have a debate about how that torque gets created. I think the disruptor in that discussion I just went through is, what if I had an electric motor? A generator. And then I had wires, and then I put thrust somewhere else. Mm-hmm. And now I actually kind of went well beyond a gearbox to just say, why not just have electric wire? But now that's a different set of problems, and I have losses, I have weight, I may have some advantages, I may have some losses. So that's what makes the whole area of aviation and propulsion fun, I would say. And it really is about having the right debates to have the right sort of set of requirements to get the right product at the right time. So it isn't really about right or wrong, it's really about what are the strengths and weaknesses. And then in view of things like fuel cost, in view of expectations about reliability. What's interesting, if you look at the aircraft industry, back in the 70s and 80s, the departure reliability. If you got on an airplane, put in your seatbelt, and said, okay, I'm gonna get to my destination, it would, I don't know the exact numbers, but it might be a 1% probability actually you didn't leave. There would be an issue somewhere, either the aircraft or the engine, that said, oh, we actually get off the airplane. Luckily, it's still safe, but you wouldn't leave when you expected to. Departure rates are now very, very, 3 nines more When was the last time you got an airplane and had to get off? So the bar for reliability has never been higher. People just expect these things to work. And that's actually a challenge when you say, well, I want to add some new technology. Because will the industry tolerate the teething pains? Because most new technology has teething pains. And you have to have the right relationship with your customer to accept that. So, that's a long answer maybe to your question, but I think it's an interesting one. I don't think there's a right or wrong answer. I just think that companies will play to their strengths and have different views of things like the future, like what's the cost of fuel, and would anybody like to look out the window and see stuff moving? Because that open rotor promotes all sorts of thoughts like that. We demonstrated an open rotor concept back in 1985 and demonstrated under a NASA program. So I think that's certainly an opportunity. But again, for that one in particular, technologists dream and talk about high propulsive efficiency, but will passengers want to look out the window and see it? Interesting thought. Other questions?
I have a question that's way back in your talk. You said that emission is regulated on the ground, no regulation on the...
For aviation, correct.
For aviation in general. So has anyone considered maybe using a dual fuel, like a fuel that's inside wherever, before starting to take off and so on? That's one question. A fuel that's more regulated, that would emit less maybe NOx, or has a low adiabatic flame temperature or whatever it is. And then you're going to be not restrained in terms of efficiency when you go upward. My second question is, does fuel change in quality based on regional? And is it a challenge, or is it something that you consider when you design? Like a certain region has a better or worse quality, or is it really regulated?
So I think your question is mostly around aviation.
Aviation, yes.
So I think just thoughts on fuel. You have to think about what fuel would you consider. So jet fuel is really a remarkable fuel. From a heating value by weight and volume, it's actually pretty close to the ideal of what you would want, even if I could design my own fuel. Just in terms of how much, if I had to carry it in the airplane for the duration of the flight, I care about its weight. But I also care about its density, because I need, if I had hydrogen, I need a way bigger fuel tank. So I love hydrogen's weight, but I hate its volumetric sort of efficiency. So you had to think about, what fuel would you want to consider, and what fuels are out there. Generally speaking, if you need two fuels, logistically that's complicated. What happens if you have one fuel but not the other one? Can you still take off? Usually we have two fuels to enable us to be more robust. But if you now said to fly an airplane I need two, that would be probably a barrier. So I think we just got to think through, and then what property do you want? The other reason jet fuel is remarkable is with the right additives, it's not that reactive on the ground. They design, and they did tests back in the 70s and 80s to look at avoiding fireballs when you have a bad landing. And so airplanes are designed to make sure that the flames don't propagate to where people could be for something like 90 seconds, which generally speaking is long enough to get people who are in a hurry to get off an airplane. So you think about other fuels, like gasoline is more volatile. It's going to be hard to meet that 90-second kind of rule. So you had to think through what that other fuel would be, was the question. I do think you raise a broader question, which is, sorry, I'll just answer the second part of your question, which is fuel quality. In my experience, fuel quality for aviation is remarkably consistent, or the engines are tolerant. So we can debate if we've made very tolerant. So either we've made such a good job that our engines are tolerant, even if they don't meet the fuel spec. But I would say fuel quality has been very good. And I will say it's not the same for ground-based applications. And so I've seen, as a combustion person, I've been exposed to fuel property issues. And usually the customer swears up and down they bought fuel to the fuel spec. And actually, they're not lying. They usually contract to a fuel provider who agrees to provide them fuel that meets these specifications. The issue is whether that fuel supplier actually supplies stuff that meets the specs. And so usually it's a pretty obvious because you'll have a failure mode in an engine that doesn't happen other places. And typically the question will be, when you have a failure, is it a design problem or is it there's three choices. Either I have a bad design, I made the parts badly and I assembled them poorly, or I'm using it poorly. But in the end, if you're doing a root cause analysis, you're trying to characterize the issue into one of those. And so typically, if once you've said, well, I've got 1,000 engines that are fine, never had this problem before, probably not a design issue, and then you get to, where the parts come from, are they assembled correctly, once you rule and say, well, we feel pretty good about that factory or the paper trail, then it gets into, say, how did you really use it? And it's hard to hide behind that, and engines usually give telltale signs of what's going on. So, yeah, aviation, thankfully, I personally, now, it's not a world I live in a lot, but I personally have not heard significant about fuel issues. So it's a good thing.
So what do you think is the biggest design factor that is limiting us from reaching higher thermal efficiencies? Is it the first row blade material?
It's a great question. I think certainly if you had better materials, that's the first place I would start. The fact that we have super alloys that we now cool and coat and all that stuff, what's next? There's been a lot of work around ceramics. And ceramics, if they're monolithic ceramics, are beautiful until they develop a crack, and then they are like your coffee cup, when you drop it on the floor. But there's a whole class of ceramics called ceramic matrix composites. And they're a little bit like fiberglass. They've got fibers and they've got binder that connects the fibers. And those show great promise. And in fact, they're reaching commercial. They've been in technology development for a long time. They're reaching commercial implementation for stationary parts. So to get to moving parts is another step of development. And the issue with ceramics is they're very expensive compared to the metals that we have today. But if you were to say, what's the enabler? The enabler is materials that can take the high temperatures without the kind of cooling technologies. Because once, I mentioned the original H turbine had steam cooling. Well, what that meant was the combustor didn't have to change the temperature it ran at. It just got the air that used to, cool the turbine. But once you said I'm going to be air-cooled, now I had to make combustion technology that would handle less air and still get the same emissions. So the trade for turbine technology gets way better if you have better materials. So I would say foundation is better materials, and that enables you to climb the curve. I think we also got to look at more system and system of systems. So, whether if it's aircraft, you start to think hybrid electric. We're seeing that on the ground. What could that mean in the air? So how do we use engine technology combined with other things? I think that's going to be a degree of freedom that we'll look at, and that could enable different performance parameters. So in any high-tech area, it's a little bit about where do you place your bets, what's the payoff if you get there. A new material is always great to talk about, but as a mechanical designer, you'll say, well, that's unobtainium, right? It's a nice thought, but is it real? I would say with ceramics, I'm seeing great progress in that area. But someone asked me over the break, when I said we went from steam-cooled H to air-cooled H, what was the innovation? And the answer was there wasn't one. It was a team sport of different technologists, each advancing their own technology in a way that delivered a much better system solution. So I think if we were to say in the future, to get to 65, to get beyond that, it will be a team sport. Now, to get to 70% ground-based, that gets into topping cycles thermodynamically. I think you got to think about what would I do with the fuel first, Because methane, especially if methane is your fuel of choice on the ground, methane has tremendous capability to be converted to useful work, and not necessarily as a heat engine, right? So thermochemical fuel cells, anyway, topping cycles can be many things, and I do think that's an area of interest. But to have a topping cycle gets into, is it worth the trip? Would someone pay for it? And it gets into all the discussions we talked about of reliability and operability and cost. So it is about better efficiency, but only at a cost that the market's willing to pay for. And so if we were in a high fuel cost world, I think the market would pay. If we're kind of in an intermediate fuel cost world right now, I wouldn't say it's high, I wouldn't say it's super low either. So, you know, it's an interesting trade. How worth it is it to have the extra 5 points of efficiency?
Hi, I would be interested, as you mentioned a few minutes ago, to hear about your views on pressure gain combustion.
Yeah, so, you know, that's one of the, you know, you asked me about what would make a big change, and I said materials, because, you know, that's somebody else's problem. As a combustion person, you said, what are you going to do to contribute to the next efficiency of cycle? And I do think the notion of pressure gain combustion is very interesting. You know, in the end, we have many practical devices that do pressure gain combustion today. They're called reciprocating engines. We release heat in a relatively constant volume. And so if you just look thermodynamically, and in fact, if you plot sort of rated efficiency versus engine size, you'll see two curves. First of all, versus engine size, they tend to have lower efficiency as they get smaller. That's a surface to volume problem. But if you plot simple cycle efficiency versus size, what you'll typically see is reciprocating engines are above gas turbines. So releasing heat at constant pressure is not as efficient thermodynamically as releasing heat in a way that increases pressure. And pressure gain combustion, one of the areas of research is looking at detonation-based combustion. There's been a couple main thoughts to have there. One is pulsed detonation, where you have a chamber and you sort of load it with fuel and air, and you have a back wall, and you allow that fuel to burn supersonically in a way that raises the pressure, and then that discharges into your work device, your turbine. Another one, and there's some advantages to that. You know, one advantage is it's a closed volume, so I really get that pressure gain. But then the question is, do I convert it to useful work? Because turbines like steady flow, they don't like unsteady flow. And then if I have an event like that, I have to repeat it many times per second. But, you know, we do that in reciprocating engines, so by itself, that's not a problem. There's a lot of activity recently in rotating detonation, and that's a more continuous process. You're basically leveraging the idea that from a heat engine point of view, I want to release my heat at high temperature. And if I take whatever I have for my engine after my compressor and I shock heat it, I get a step change in temperature. So if I release heat at that elevated temperature, I now have potential to do more useful work, and that could be a step change in performance. So that's a basic idea between why I would consider pressure gain combustion. There's a lot of basic physics to work out, and there's also some basic questions like, can I get this mode of combustion with practical fuels and air? That's kind of important, because if it works on hydrogen but nobody has hydrogen, it's just an interesting idea. So I think that's a key question to be answered. And then it gets into, can I package it in an engine? Can my work extraction device, like my turbine, take what this combustion device would give it? And then it gets down to questions like, what are the emissions? Is it noisier? A lot of questions. So I think as a research topic, it's very, very important. And I think as you start to think about more practical, the real question is what application would be first? And where would it pay off first? And kind of what's the lowest risk application to think about? So very active area of research by many groups around the world. And I think it's an area that you know, I'm certainly very interested in.
Thank you very much.
So thank you for the talk. I have a question regarding combustion instabilities. And so my question is, what is the GE approach on this problem? Because you show us that you always do like simulations, LES, but you also do experiment. Since this problem is strongly dependent on the geometry and on the system itself, how can you cannot like test the entire gas turbine system and then see that it's unstable? What is the GE approach on that?
So, you know, combustion instabilities are one of the challenges of the last 20 years for combustor designers. And it's been something that I think every engine manufacturer has faced into. They've had to face into to meet the emissions regulations. We've had to understand it. There's not one approach. I would say there's many layers to how you think about that problem. And while you don't want to have issues in front of customers, I think I can quote products from every manufacturer where that's actually been true. And so this actually has hurt the reputation of gas turbines. And certainly in the 1990s, if you're a utility owner, do you want to buy a gas turbine and maybe have this issue, or do you buy something else, a coal plant or a nuclear plant? Well, probably not nuclear, but they looked for other solutions. I think the industry has figured out a lot, and technology and the great work of thousands of technologists around the world has really helped. What I can say is it's that this is a set of nonlinear physics that is able to. The worst thing to do is to feel confident, because nature will humble you in a second. So I will not say we solved the problem of dynamics. I will say that I feel good about managing it, and I think the industry manages it, and at all levels. It starts with the fundamentals to understand the root cause. Do we have design tools? Do we know what to look for when you're doing validation? I showed you the walk of what can you do in a single nozzle rig and so on. Just tremendous. On every front, I've seen tremendous progress in the last 20 years. So I would say the probability of a visible problem to a customer is lower, but it will never be zero. And partly because customers don't always do what you think they're going to do with the machine. And in the end, they bought it, they own it, they can do what they want with it. So this is really about the right relationship between the equipment provider and the owner and the operator to work together. And I'd say what I'm observing, and the thing that I feel really good about is I'm seeing more connection between OEMs and their customers. We're seeing a tremendous amount of work on the digital side of being connected. And the more you can be connected, the more you can have information flow. And then you can get to the point where you can start to say, maybe we're heading into a problem. So it's everything from the basic design, the basic principles. I think we know a lot more now than we did certainly 20 years ago. But it's also, even when you have a piece of equipment in the field, do we know, are we respecting it? As it wears out, how does it wear? What does that mean? So it's very deep. We could spend a week just talking about combustion instabilities and how you manage it. But I will say it's part of what makes the area of combustion really exciting. It keeps you on your toes. I think we're almost done. I see Manny up here.
So I think I speak for everybody here to say that, Dr. Dean, you really did an outstanding job. There's very few people, many of us know, that have worked in industry for so long, but still understand the fundamentals, the applications of those fundamentals, and tie the two together to really make impact in all of society. And you really articulated that to us today. As an organizer of the event, you could not have done a better job. You made me really happy. I can see from the students' perspective, they were really engaged. So thank you very much for the efforts you put into this.
Well, thank you very much.